understand I freaked a few of you guys out with my top secret emails yesterday. Oh, we don't have AirPods on, so nobody can hear me. The top secret emails that you received, or maybe received, those messages will self-destruct in 15 minutes. Now, it's a reference to an old TV show called Get Smart. You guys are pathetic. That message is what you need for assignment, I think C is the name of it. So where I've diabolically encrypted some things and you guys have to figure out how to crack it. And they get progressively more diabolical. So, yeah. Okay, so I wanted to talk about another encryption method called the substitution cipher. And in some sense, the Caesar cipher is an example of a substitution cipher, but a substitution cipher can be more general. And for the assignment B and C, I've come up with three different encryption techniques. The first of which is the Caesar cipher, which we've already looked at. So that one will be easy. And then a slight generalization of it, which I'm calling Evil Caesar, which is a little harder, but not as good as the Visionaire cipher, which is outright diabolical. Okay, but not as diabolical as, say, the German Enigma machine from World War II. That would be even more diabolical. And maybe eventually I'll turn you guys loose on that one. Anyway, so the Visionaire cipher is it was called for many years the indecipherable cipher, and of course that's not true, right? We've been able to crack it since the 18 whatevers. But I think you guys will find that to be an interesting challenge. The other ground rules here, you can find decryption and encryption websites that will try and brute force it for you, but that kind of defeats the purpose of the assignment. So don't use other people's things. Try and figure it out yourself. And lives are at stake, gentlemen. So yeah. Now, as you guys work through B, but especially C, keep track of what you're doing and how. And because you remember at the very beginning of the semester, I promised that all of you guys would have to sit through technical interviews. And I'm going to have you guys also write a technical report, right? So we'll do that over the assignment C, basically, the diabolical decryptions. And so keep track of what you're doing, because that will help you in terms of writing a report and the technical interview. Anyway, so, right. So for the substitution cipher, we're going to write this and we're going to use a different tool than we've used before, which is called a dictionary. So a dictionary is a data type where essentially you have every entry in the dictionary is somehow a pair. A first thing called a key, and a second thing, which would be the entry that matches that key. So, for example, the book's example does something where they've got, they use a dictionary to store inventory of a number of fruits. So you could say, all right, I've got 5 apples and 10 oranges and 7 bananas or whatever. You could use a dictionary to store that. And the first entry for every pair would be the name of the fruit as a string. And the second entry in every pair would be the number of those things. But then you can match things. And if you ask, okay, what is dictionary of apple, it would return the number of apples. Okay, so it's a way you can kind of pluck out pairs of information. And one application of a dictionary would be to encryption. It's not certainly the only way you could do things. So the idea behind a substitution cipher is, well, let's think about what the Caesar cipher did. We just shifted the alphabet down however many letters, okay? And if we shifted it 0 letters, then of course we got no change. So a substitution cipher is the same idea, except we don't have to shift all the letters. We could take the regular alphabet and just jumble it up however we want. Okay, so that means, of course, that there are a lot more different orders that the alphabet could take. With the Caesar cipher, how many different orders of the alphabet is possible? 26, because you could start with the regular alphabet. You could shift it by 1, 2, 3, dot, 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 up to 25 letters, or 0 letters, which would be to leave it as is. So 26 possibilities. Whereas if I randomly reorder the alphabet, and do like A, Q, B, Y, D, T, O, right, where I could just jumble the letters however I want, how many different possibilities are there then? It'd be 26 factorial, which is a very big number, okay? And factorial, if you don't remember, would be, so it'd be 26 times 25 times 24 times 23 times dot, 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 down to 1, which, just for sake of edification, what is that? Let's open up Wolfram Alpha. It's going to be a very large number. Yeah, so good point. Which is to say, in this 26 factorial, it's possible that some letters map to themselves, which you could allow or you could disallow. That's up to you, right? If we don't disallow it, so if we're perfectly content that it might be the case that a letter maps to itself, then there are that many possibilities, okay, which I think you guys would agree is a very large number, okay? So brute forcing a substitution cipher is not exactly going to be practical in most cases, okay? Now, Thomas brings up a good point, which is in an encryption scheme, do you ever allow a letter to map to itself? Well, you have to make a decision about that, yes or no. And let's take the German Enigma system, which is an example of a substitution cipher, although it's much, much more complicated than just sort of a regular substitution. In the German Enigma system, no letter could ever be mapped to itself. And that actually was a vulnerability of the system, because if you had a letter A, for example, in a message you captured, it didn't come from a letter A. It came from something else, and that could allow you to crack it, or at least have a hint that if you could figure out that, all right, this isn't a letter A and the next thing isn't a letter Q or whatever, then eventually maybe you could decipher something. And the reason that was the case was just the way that the Enigma was designed. Okay, but for our purposes, right? It could just be the alphabet here will be the alphabet A through Z, but scrambled up in any way we see fit. Okay, it could be just rotated as in the Caesar cipher, in which case we'll get the exact same result as the Caesar cipher, or it could be jumbled up in any one of those 26 factorial ways. Okay, okay. So what I'm going to do is I'm going to start by making a list, and I'm also going to make the plain alphabet, which I'll make as a string, okay, which is this. And we'll see why that'll be useful in a moment. So that's the alphabet just in the regular order. And then I'm going to make a list by pairing up each letter of the regular alphabet with its corresponding entry in the new alphabet. Okay, so the new alphabet would be some alphabet that's all jumbled up. Okay, so A will map to whatever the first letter of the alphabet is, B to the second, C to the third, and so on. Okay, so the first thing I'm going to do is make a list of this, and I'm going to call it dict list for dictionary, and it's going to start empty at the beginning, and then I'll do for I in range from 0 to 26, because there's 26 letters in the alphabet. No, because there's 26 letter in the alphabet, but I'm starting at 0, right? Okay. And I'm going to append the following thing to it. I'm going to append a parentheses object called a tuple, okay? And the tuple, in this case it's a 2 tuple, will have in it plain alphabet of I and the alphabet of I. Okay, so a tuple here is an ordered pair of things. In my case, they're going to be letters, which is to say 1 character long strings. Think of a tuple the same way that you think of an ordered pair in math class, right? You have a first coordinate, you have a second coordinate, and in math class, they're always numbers, okay? You could have the 0.3 comma 7, and the 3 is in the first coordinate, and the 7's in the second coordinate. Well, do they have to be numbers? In math class, they were, because they're referring to geometric things, but could you have an ordered pair of A, comma, B? Sure, okay, and that's what I've constructed here. So the first entry of each of these tuples is the whichever letter of the alphabet, the regular alphabet, okay? So A, comma, what's the jumbled version of A? B, comma, who's the jumbled B, and so on, okay? Is that okay? And then I'm going to turn this into a dictionary in the following way. Okay, so, and the encrypted string should be a string, not a list, so my bad. Okay, so then I'm going to do dictionary equals dict of dict list. So what this will do is take the list of ordered pairs and turn that into a dictionary object. And I'll print what these things look like in just a second for sake of edification. So a dictionary, you can think of this as, it is a data type in the sense that it's a sort of a collection of pairs, but in some sense it's also a function, meaning I could ask, what is the dictionary of something? And if I ask, what's the dictionary of A, it will return what's scrambled A. Okay, so it's kind of a function, but it's kind of in some ways also a list at the same time. Does that kind of make sense? Yeah, and we'll see this in action in just a moment. Okay, and then I need to actually go through and do the encryption. So I'll do that as follows, and this part should be this should be a plain string. I'm just going to go through letter by letter in my string that's passed to the function for encryption, okay? And I'm going to concatenate onto this thing dictionary of plain string of I. Okay, so let's think about what that statement means. My encrypted string starts out with nothing in it, right? So I start with a blank slate. And each time I go through this loop, I'm going to tack a new letter onto the end of it. Okay, so what letter do I tack on each time? Well, if plain string of I is, that's going to be the letter of the actual message, right? So let's say that the message is Wabash always fights. Plain string of 0 would be the W, okay? And then I'm going to say, all right, dictionary, what does W get mapped to? So what's the scrambled version of the letter W? I don't know, but dictionary of that thing will return to me, okay, W maps to G, say. And so then I'm going to tack a G onto the end of my encrypted message. Does that make sense? And then just keep going until I run out of letters. Okay, so is that good? All right. So once that's done, I'm finished, and I can just return this encrypted string, which yeah, I already had the return statement. Okay, so let me make a little bit more room here so you can see the entire code at once. All right, so that's the whole shooting match. Okay, so what would happen if I gave this thing a message with the regular alphabet, A through Z, in the same order? It would return exactly what I gave it. So that's not particularly useful for an encryption, but for a sanity check, just to make sure our function isn't garbage, why don't we test it that way? Okay, so for example, let's make, all right, how about the quick brown fox jumped over, oh, okay, the other thing is, have I put anything in here that's going to deal with spaces? I have not, so I'm going to remove all of the spaces. And I've done that in the secret messages that you all received. You've noticed that there's no spaces. You'll have to, like, once you decrypt it, it'll be obvious where the spaces need to go in the message. But yeah, has anybody figured out their third message already? Not the right way. Yeah, you used some online thing and figured it out. Ah, well, you cheated, right? Yeah, I want you to figure out how to do it without using the online thing. You have to write your own thing, huh? Lives were at stake? Yeah, well, yeah, your grade's also at stake. Maybe I should have put that in the, right? Okay, so, oops. So I'm going to, just for sake of testing, oops, I'm going to start with the alphabet being the usual order, and then we'll scramble it up somehow. Okay, so if I do say something like, all right, what did I call this? Substitution encrypt, and I need to pass this my string and my alphabet. And then I'm going to print um, the plain text string and the ciphertext string, and then let's see what we get. All right, so survey says, okay, so what did I get? What was the original message? The quick brown fox jumped over the lazy dog. And what was the encrypted message? Yeah, the exact same thing. Okay, why did this happen? Yeah, because I just used the exact same alphabet. So it replaced all the A's with A's, all the B's with B's, all the C's with C's, and so on, and therefore it didn't actually change the message. Okay, does that make sense? Yeah, Mark. Well, you fail. Okay. Lives are at stake, Mark. That was my bad at the beginning. That should be a string, not a list. Yeah. Yeah, so the error Mark had was I had fixed it, but you might have missed it. So at the beginning on line 3, I had a double brackets there, not quotes, but it's a string, not a list. So I should have had quotes. Okay. All right, good. Okay, so obviously this is not a useful encryption with this alphabet, right? But what could I do to this alphabet here? Well, I could jumble it up somehow, right? Okay, so how do I want to jumble this thing up? Yeah. Okay, so I could do something like that where I do a definitive pattern, do B and then E and, or not E. Yeah, no, E. No, that's one, two. Well, I'd go to F next, but whatever, right? I can jumble them up however I wish, right? So, in fact, what would maybe be a, how about, I think there's a reverse function. I could do a random. That's actually even better. So let's do that. Let's come up with a random ordering of the alphabet. Okay, so how am I going to do that? Well, that's a good question, right? So, because what's the issue if I just start randomly picking a letter? I could end up with the same letter twice, and that's forbidden because I can only have one instance of each letter in my substitution alphabet. Okay, so if we're going to come up with some sort of random scheme, we have to make sure that we never accidentally duplicate a letter. Well, we're definitely going to have to do a loop with some sort of if statement. Okay, or if we're clever about this, we could, well, can I pluck a letter out of a string? Yeah, I could replace it with a nothing, right? So every time I use a letter, let me replace it in my alphabet with a nothing, and then the alphabet will eventually be empty. Okay, so let me call this, say, new alphabet, and let me start with an empty string, and then let's build up this new string by that method. Okay, so in this case, how many letters do I have? Well, 26, right? So I can do for I in range 0 to 26. And I'm going to do, well, here, let me do this. First off, if I want to do random numbers, what do I have to do? Yeah, I need to import random, so let me put that up here at the top. Okay, I need the random package from Python. Okay, and then let me do the following. So let me do random number equals, um, oh, this is really nice. Okay, you guys are gonna hate me. Okay, so I need to get a random number, and my random number needs to be in the range from 0 to 25. Okay, but why did I put 26 minus the length of new alphabet? Okay, so at first, what's the length of new alphabet? On the very first time I run the loop, the length is 0. I haven't done anything yet. So 26 minus 0 is 0, and range 0 to 26 is the number 0 through 25, and everything's good. That would also work. Okay, so I can do this one of two ways. I can either think of it as being 26 minus the length of the new alphabet, and as I keep tacking on letters to the new alphabet, then it gets longer, right? Or, as Thomas suggested, instead of 26 minus the length of the new alphabet, why don't I just do the length of the old alphabet? Which one makes more sense to you guys? Okay, that certainly is a logical solution. So let's do that. Okay. Now, the reason it has to be something that depends on the length of the alphabet is because let's say that my random number generator picks 25. What does that mean my first letter is going to be in my new string? Z, because A is 0, right? Okay, so if I use the Z, then the next time, how many letters do I have to pick from? Only 25, which would be ranged from 0 to 25. The numbers 0 through 24, because I've already used one of them. Does that make sense? Okay, so this will get me a random number. And then using that random number, I'm going to do new alphabet equals new alphabet plus, so I'm going to concatenate on, my alphabet of the random number. Okay, and then my alphabet I need to replace whatever the corresponding entry is with a blank. Okay, so if let's say that the random number generator picked a 10. Okay, so I would pluck the 10th letter out of the alphabet and tack him onto my new alphabet, and then delete him from the old alphabet so I don't accidentally reuse him. Okay, is that okay? All right, now here's a subtle question. Why did I generate the random number on line 23 and then use it on line 24 and 25? Couldn't I have just done random.randRange both on lines 24 and 25? Hold on, put your hand down. Somebody else. Why did I generate the random number once and not twice? Well, that kind of gave away the answer, didn't it? I could get different numbers, right? And I probably will. Okay, so the reason that I called the random function only once on line 23 is because the number of the alphabet that I need to pluck out and delete from the other alphabet need to be the same value. So I only need one random number here, not two. Okay, does that make sense? Yeah? Okay, so line 24 will add the corresponding letter to my new alphabet. Line 25 will delete that letter from the old alphabet so I don't accidentally reuse it. Okay, is that good? Okay, and then when I go through 26 of these, because that's the length of the alphabet, then when all is said and done, new alphabet will have 26 letters in it, and my alphabet will have nothing in it. Yeah? Okay, so let's make sure that that happens and just see what random results we end up with. All right, so I'll print my alphabet and, and I'll print new alphabet. And let's see what happens. Error. Oh, I know. It's because I then gave, I need to comment this out. I was trying to use the old alphabet for the encryption. Okay, so I get this, which is my alphabet randomly scrambled up. Okay, first off, huh? Yes. Okay, which makes sense because what's the old alphabet now? Empty, right? So that's why I got a blank line. Okay. First off, then, looking at the alphabet that I got, are all the letters present? And did I accidentally reuse any of them? Well, right. So point being, though, did this actually work, right? Are all the letters there? I didn't miss any letters, and I didn't accidentally reuse any. Okay. Which, looking through it, yeah, I'm pretty sure it's good. Okay. So then, if I want to use this for encryption, then what do I need to change here? Instead of my alphabet, what am I going to use this time? New alphabet, and then I'll print these, and let's also print that. Okay, and so we'll encrypt with the new alphabet this time. Okay, so because I was using a random number generator, right, every time I run this program, it's going to give me a different randomized alphabet. And if you want to use the same randomized alphabet, then you better write it down or store that someplace. And there you go. Okay. So the quick brown fox jumped over the lazy dog turns into that completely jumbled mess. Okay. And just for sanity check, in a substitution cipher, and this is one of its weaknesses, the same letter always ends up as the same new letter. Okay, so for example, what's the first letter of the original message? T, right? T got mapped in this case to a W. What about the other T? Also a W. Okay, or what's another letter that appears a bunch? How about the O, right? So the O maps to the C in brown. It maps to the C from fox. It maps to the C from over, and it maps to the C from dog. Okay, so in a standard substitution cipher, a given ciphertext letter always came from the same original letter in the plain text. Okay, so what do you think that means if you were trying to brute force or reverse engineer that one of these? Do you have to check all 26 factorial possibilities? Can you kind of maybe rule out some of them, or like go to, yeah, like, so how might that be a vulnerability of this system? Just think. Hmm? Okay, but yeah, so still elaborate. Like, how is this a weakness that the letter mapping is constant? Anybody but Thomas. Sorry. Yeah. Yeah, exactly. Letters that are more frequent in the regular English alphabet are going to be more frequent in the ciphertext also. Yeah. Which you could do, right? Now that's a more sophisticated cipher, right? But for example, what are the more common letters in English sentences? E, okay, RLS, what is it on Wheel of Fortune, right? When they get to the final thing, RLST or RLSTE something. I think that's it. You guys know what I'm talking about, right? Though, um, this kind of reminds me. So back in the day, let's say you had to stay home from elementary or middle school. You were sick, right? What were the necessary things for you to survive a day staying at home being sick? See, for me, it was a Sprite, saltine crackers, and The Price is Right reruns on TV. Okay. Yeah, because not, or maybe ginger ale instead of Sprite, one of the two, right? Um, okay. So, all right. So does this work? Yeah. Now it's vulnerable. Yeah. Question. All right. Let me take a look. You fail. Pretty sure it's right there. So
set to 0. Unless I forgot. Blanked.
Oh, you want to use the new alphabet here,
Oh.
right?
Yeah.
Because the old alphabet has nothing in it when we're done. Yeah.
I can figure it as well. Actually, we used somewhere else earlier, but with the function online kind of thing.
Okay.
Out of range. And then it didn't like dictionary plain string I either.
So here you need to pass it new alphabet, not my alphabet.
Okay.
And then that'll fix it. Because my alphabet is empty by the time you get there. Yeah. So same error. Yeah. So notice on line 31, right? What alphabet do I need to give to my encryption function? Not the original one, which is now empty. I need to give it the new one that's all scrambled up. Okay, and now it works. Okay, well, that's probably a typo or something. What does it say?
It's this part again, the dictionary plain string I.
Let me see. I don't see any obvious errors. I'll run it again.
That was the one that had shown up.
Before.
Yeah, I kept getting that error until this one showed up the last time.
Oh, here? Oh no, that should be okay. Oh, right here? Oh no, wait. Okay, I don't see any errors.
I was trying to compare it with what you had.
Yeah.
I couldn't see anything, but not really sure.
So the error got called in this function when it got, so that's where the error is line 15.
Yeah.
Encrypted string equals encrypted string plus dictionary of plain string of I. Okay, I don't see anything wrong. Yeah, let me look at it more later because I don't see an error. I'm probably just being an idiot, but okay. So anyway, so what's the weakness here, or a major weakness? Well, two major weaknesses. Every letter always goes to a given letter of English always goes to the same encrypted letter. Okay, and that means that in the case of, say, the letter E, which is common, in our ciphertext, we would expect to see Q equally common as E is on average in English. Okay, so what would be a maybe more diabolical way to do this? What about if you change the substitution every letter that you go through? That's essentially how Enigma worked, by the way, is that every time I encrypt a letter, the alphabet that I use to scramble changes. Now, it changes not randomly, but in a very predictable order, okay? Because if it were truly random, how would I be able to communicate with somebody? Like, if you're going to decrypt the message, let's say that I'm sending you the message, right? Then what do you have to know? So let's say that I want to send Thomas, the message that says, I don't know, one does not simply walk into Mordor. Okay? So I'm going to encrypt, one does not simply walk into Mordor. and I'm going to transmit somehow to Thomas that message. How is he going to decrypt it? What does he need to know? He needs to know the scrambled alphabet that I used, okay? Which means that somehow I have to communicate that to him, and either I have to give that to him in plain text or I have to encrypt it using a different scheme, okay? Now, in the case of the German Enigma machine, the way that they would do this is the order of the letters that got jumbled was not completely random. In fact, it was very deterministic, and it had to do with which disk do they put into the machine in a different place and what was its initial setting, and they would transmit that in the clear at the beginning of the message, or make references to an entry in a code book that would be updated in the fleet over the course of the war, and right, so it got more and more diabolical. And then the German Navy used 4 rotors, and yeah, it got really, really evil. Okay, okay, but this proves, or the reason I picked this as an example is 2 reasons. One, because we've made a dictionary, right, and we've used a dictionary, and 2 is because it's another encryption scheme, and since I don't know, maybe you guys are going to get tired of encryption as an example, but that's assignments B and C, right? Is to deal with encryption. And who knows, maybe there'll be more assignments, right? No? You don't like these assignments? They're good? Yeah, they're character building, right? I'm building great character with these assignments. Okay, so let's say, for example, you wanted to store you wanted to store that plain text, or sorry, not the alphabet. You randomly generate the alphabet, and then you want to reuse that key over and over again. What could you do to preserve it? Put it in a file, okay? And in fact, when I sent you guys those random messages, right? Or let me show you this one. This one is not top secret. It's been declassified because I thought in my mind it is declassified, and so now it's declassified. Jacob, you see what I did there, right? I said this file has been declassified because I thought in my mind it's declassified, and so now it's declassified. Okay. Yeah. Okay. So what did I do? Well, for the purposes of the assignment, okay, you obviously it won't work here because McKinney encryption library is not in that folder, and the reason it's not in that folder is because it is classified. Okay, so what did I do? I wrote my encryption library that has my Caesar, Evil Caesar, and Vernier ciphers and their corresponding decryption functions. And then I made a list of words, okay, which is here, and I just got a random list of words off of, generated a random list of 200 words, or 199, I guess, right? And then my test is going to make a message that has a bunch of random words smushed together. Okay, so a random number of random words smushed together. That's the message. And then I picked a random number for my Caesar shift amount, and then I encrypted it, and then I dumped all of those to the file. Okay, so for example, if you look at Caesar.txt, these files, by the way, are what you're going to test your encryption and decryption methods on in assignment B using assert statements. Okay, so responsible, oafish, inquisitive happen with a Caesar shift of 17 gets encrypted to that jumbled mess after the comma, right? So I just generated basically 100 or 200 random messages, randomly encrypted with the different Caesar method and evil Caesar and the Vernier, and you get this. Okay? So you guys get to use those test files, because what should happen if you write a Caesar encryption and you give it responsible, oafish, inquisitive, happen, and 17? What should you get? That. And if you don't, then your function doesn't work correctly. Okay, does that make sense? So making sure your functions work correctly is, of course, key to the next part of the assignment, which is to try and try and outsmart me and decrypt the secret messages I sent you, where you're going to use your decrypt function. So if I use the decrypt function on the jumbled mess at the right with the key 17, what should I get? Responsible, oafish, inquisitive, happen, right? So you test the functions both ways, right? Because you should be able to both encrypt and decrypt. Now, in the case of Caesar, encryption and decryption are almost the same. If you encrypt with 17, then you decrypt with two ways of thinking of it. Either negative 17 or 26 minus 17. Same thing, okay? And then for the evil Caesar, that one you have two shift numbers, okay, because I've been diabolical. And then for the Vernier, you have a second word, which is the key, okay? So here, if I wanted to transmit to Thomas, juice, clammy leg, that's my message. I'm going to transmit it using the key functional. So Thomas and I would have agreed in advance as to what the key is. And so he would know that the key is functional, and I would know that the key is functional, and I would use the procedure and generate that jumbled mess. Okay. Now, what's nice about the Vernier cipher is, notice the first two letters of line 3, juice, J-U, but what about the ciphertext? So not always does every letter go to the same thing. Aha! Right? Good question. How is the word used as the key? Well, if only there were a website where we could type in things that we're interested in finding out about, and it would tell us. So they give an example, but here's the formula, right? Okay, so quick question. When you see mod 26, that's a mathematical way of writing it. What's the equivalent programming? When you see mod, you should think, no? The remainder operator, which is the percent thing in Python. So the percent operator gives you the remainder upon division by whatever. So why is it always mod 26 here? Because there's 26 letters in the alphabet, right? Or at least in the English alphabet. Okay, so that's basically the formula for it. And yeah, so y'all's job, of course, is to figure out how to implement this. So they give several nice examples, and of course, I've got 100 more of them in that file for you to test with to make sure your function works correctly. So the mod operator is going to be very helpful. The remainder operator is going to be very helpful for that assignment. Okay. And for those of you where are my math majors, or going to be math majors? None of you? Why would you do that to yourselves? Because math is the second easiest major on campus. You know what the first easiest major is? Physics. because you're just studying the universe that you live in. How hard could that be? No? So what is the easiest major on campus, do you guys think? History, religion, rhetoric? Yeah. Econ, pretty easy? Yeah. Okay. Anyway, but if you're interested in some of the number theoretic and mathematical descriptions, it gives a nice treatment of it there. And this method of encryption is relatively old, right? So 1553, right? And of course, he didn't have a computer to do this. So the actual act of encrypting and decrypting was a much slower process, but the algorithm is exactly as we've described. It's just our computer can do it super fast. And if you didn't have a computer, this would probably take forever to try and crack, which is why people called it le chiffrage indéchiffrable, or indéchiffrable, right? The indecipherable cipher. Oui? Yeah? Anyway, so cool. Yeah, so giving you guys a diabolical assignment. Okay, now the dictionary thing, right? I've used this, so let's go back to our code, right? This was an example of using a dictionary. Where did I put this here? Using a dictionary in order to map letters. So you might ask, why didn't I just use the replace function instead?
Because then you might replace this multiple times.
Right, and that's the problem. Okay, so for example, let's say that I look at my first letter, the Q, and I replace it with an A. Well, now my message has a new A in it, but it also might have still had other A's that I have yet to deal with. And if I replace all of those A's with a F, well, some of them need to be replaced with an F, but not the one that I started with. Does that make sense? Okay, so using the replace function would be a bad move here, which is why the dictionary is a better method, or in this instance, right? Now, maybe if you thought about it, you could also use the replace method by re-engineering it, right? That's certainly possible, but the dictionary was a good tool here, okay? All right, so what's the assignment where I want you guys for certain to use a dictionary? How many guys have looked at the assignments? I post them. I slave over a hot stove all day to post these diabolical assignments, and you guys don't even read them. You'll look at it the day it's due? Thank you. Thank you. Okay. And on the subject, actually, of due dates, I'm going to get on my soapbox for a minute. The number of people who are not submitting something by the due date is too damned high. Okay. I expect that you guys submit something by the first due date. Right. Now, if it's the day after 1 week because you've got an exam, no big deal, right? But what happens if you wait and your initial submission is the day it locks on Canvas 20 minutes before it locks on Canvas, looking at you two in the back? Okay, what happens? If you screw something up, guess what? You get a 0 because you don't have time to fix it. Okay, so don't be that guy. And you guys need to stop being that guy. Got it? Okay. Because I guarantee you that it may work on one assignment or another, but there'll be dragons coming up ahead. Okay, so assignment A, which is assignment 10, but I'm counting in hexadecimal because I'm a nerd, okay, is open a plain text file and using a dictionary, translate it into pirate, okay? And here is an example starter dictionary of pirate phrases. So for example, where do you go to the bathroom or the restroom if you're a pirate? You go to the head. That's a naval term. Okay. And why was it called the head back in the day? Because it was at the head of the ship, right at the front, right at the bow. There'd be like a couple of seats with holes cut in the wood that would just dump right into the ocean. And that's where you do your thing. Okay. And to this day, aboard ship, it's still called the head out of tradition. Okay, so what about professor? Professors are foul blackguards, okay? And hotels or dorms or frats are definitely Fleabag Inn, right? And students, well, you guys are swabbies, right? And the restaurant or Sparks is the galley, right, where you get your food. And I don't know, can you guys think of other things that I haven't put up there of pirates? I mean, if there's not some R in there, then it's not truly pirate. And I know we're about several months after International Talk Like a Pirate Day. That would be really appropriate if I was assigning this on that day. No? What? Huh? What am I on? To translate, to take some text and translate it into pirate? I'm allowed to nerd out. I get paid to nerd out. You guys all pay me good money. You pay this college very good money so that they can pay me not so great money to nerd out. Okay. Okay, so there's your starter dictionary. Have some fun adding a few things to it, but keep the swashbuckling to mostly clean level, you barnacles, you, right? But you guys all watch SpongeBob, right? So you should know all kinds of nautical phrases, right? Like what kind of things were in SpongeBob that might be sort of pirate related? Seriously? Well, yeah, or Davy Jones' locker, okay, or something. Okay, so have some fun adding some things to the dictionary besides just the examples that I've got. And what's the whole point of this then? Take some plain text that can come from wherever, okay, and that's going to be your input.txt. You're going to open that file and start pulling in lines and replacing the words. Not all of them will get replaced, obviously, but replace the words with their corresponding pirate translations. And hopefully at the end of it, your output.txt is kind of funny because it might be, oh, I don't know, the beginning of A Tale of Two Cities, but now in pirate. And I don't know, that just seemed fun to me, right? Yes?
Could we like write something ourselves too, or should it be like a pre-written text?
Oh, you can write something yourself. That's fine too. Yeah. That doesn't matter to
I
me.
probably won't put that much work into the assignment. No, I just figured I'd ask it.
Yeah. Yeah. Okay. So anyway, find some text. Get a good 500 to 1,000 words of something that it can be kind of whatever, and then go through and obviously like your dictionary. If we got, for example, the first 1,000 words from A Tale of Two Cities, I doubt very seriously that the word professor or uh, restroom appears there. That's probably not really within. I mean, restroom. I don't know. I don't know if Dickens would have used that phrase. Okay. So anyway, you may need to adapt the dictionary a little bit for whatever text that you're starting with, because of course this whole exercise is lame if none of the words in your dictionary actually appear in the text that you're working with. That's no fun, right? Okay, so yeah. Now, what you guys will do, of course, is don't include your output.txt because I'm going to run your program on your input.txt, generate what your output is, and then compare the two. And if it looks pretty piratey, then you get a piece of 8. No? A piece of 8? It's a gold coin. Oh, you guys are pathetic. You're all pathetic. Yes? Okay. Especially while I'm streaming. Okay. Got it. Okay. So, right. Hopefully you'll have some fun with this, but the key is that you're working with dictionaries, right? That's the key part of the assignment. All right. Now, for assignments B and C, those are, of course, the really fun ones. Okay, this one's a lot longer. So I wrote McKinney Encryption Library, and in it are nothing but function definitions. That's it. And also an import random because I needed that. You guys are going to do the same thing. You're going to make an encryption library that's going to have within it 6 functions. Caesar encrypt, Caesar decrypt, evil Caesar encrypt, evil Caesar decrypt, and then the Vigenere, which I just realized I made a typo on the name of it. It should be Vigenere, not, yeah. The other thing is Vigenere has an accent on one of the E's. Do not put that in the name of your function. Just type it in regular. In a report or something is where you would put that accent in. Okay. So these things are going to accept values and return values as described, and this is really critical. Name your functions exactly the way I specify them, because the unit testing, right? So when I generated y'all's, 100 examples of encrypted text, I also checked if I decrypt it, do I get the regular text back? Do they match? And so I had an assert statement that went through all of these things and made sure that they matched. And that's how I made sure that my functions were correct before I gave you guys this stuff. Okay. And for you guys, you want to test it against my examples. And if it passes all 100 tests for each method, then your function is probably fine. Okay. Okay. So the 2 important things: name the functions exactly as I described them. The second is your library file must have nothing but function definitions in it, no other code. And what that means then is I can import your library, and if I import your library instead of mine and hit the button, it should work exactly the same way because I'm calling your instances of the functions instead of mine. And if your functions are written correctly, they may work differently to get the solution, but they're still going to spit out the same output. Okay, and if they do, check, it works. And if not, then you fail. Okay, all right. Then assignment C, and here's where I want you guys to try and be creative. Right? So I've given you messages that I've encoded using those 3 methods, and it's your job to figure out how to crack them, to write programs to assist you in the cracking process. Okay? Which means no using other people's cracking programs, Mark, that you might find online. I did. It's all right here in the assignment. Yeah. Well, okay, because look, I'm not particularly interested in whether or not you can Google and find a website that can decrypt them for you. What I want you to wrestle with is to figure out how the hell to do it yourself. Okay? Because that's what I'm going to ask you about in your technical interview, and that's what you're going to write about in your technical report. So you better figure that out, and it better not be, hey, I Googled this thing, and somebody else did the problem for me, right? Because you know what they didn't have in World War II? Google. right? They had to figure it out them damn selves. Okay, so what's evil though is you guys don't know what the original message is. You know how long it is because the encrypted text is the same length, but you don't know what shift amounts I used. And for the Visionaire cipher, you don't even know what key I used, and you don't even know the length of the key I used. And what's worse is everybody's numbers and keys are different. Okay, so even if your buddy figures out his key, that's not going to help you figure out your key. Okay, it's almost as if the professor randomly generated a bunch of keys and then used random keys for everybody's assignment and has a top secret list on his computer that's not on GitHub that you guys can't access. Okay, now in true World War II fashion though, if you can manage to break into my computer, okay, or my office and get the appropriate stuff off of my computer, that will constitute a win, but good luck. Okay. And a $5 wrench attack is not appropriate under the gentleman's rule, so you can't do that either. Okay. You guys remember the $5 wrench attack from last week, right? Okay. Yeah. So this assignment is, of course, top secret. You are not to discuss it. It's mere in existence with anybody but me. That includes the QSC, by the way. Okay. And you also should not leave copies of this assignment laying around at any current or former president or vice president's house, should you be visiting one of them. Okay. Just saying. Yeah. Future ones? No, because they don't have clearance yet. Okay. And if you can predict who's going to be president 10 years from now, then you might want to talk to those two about sports betting, okay? Because you can make yourself a handy chunk of change, I suspect, okay? Okay, so you're going to have your encryption library along with anything else that you generate code to solve the challenge, okay? And I'm going to warn you, the Vernier cipher one is going to be hard, okay? And in fact, it may be impossible. We'll find out. Huh? It should be possible. Okay. All right. This is probably a good place to quit for the day, and I will see you guys on Thursday.